We're going to continue our lecture on light, and in this week we're going to talk about light rays and how they produce images in flat mirrors and curved mirrors. We'll talk about the law of reflection and angle of incidence, angle of reflection, and talk about specular versus diffuse reflection. So two types of reflection. All right, so to begin with, the ray model of light. So we're going to have a few things to write down here. Light rays travel in straight lines. There's the first one. So you can go ahead and jot these down. Light rays can cross each other and they don't interact with each other. A light ray travels forever unless it interacts with matter. An object is a source of light rays. So in this chapter, we're going to draw something called a ray diagram, which is a simplification of the light rays coming off of a source, because there's an infinite number of light rays coming off of a source, but we're only going to draw so many. So rays originate from every point on the object, and each point sends rays in all directions. Your eyes see by focusing a bundle of rays. Okay, so this is all we're grouping all these ideas in the ray model of light. Okay, so when we have a source of light rays, an object can be either luminous or illuminated, right? And so a luminous object, a self-luminous object, directly creates light rays. Some examples of these are light bulbs, the sun. Reflective objects or illuminated objects reflect rays that originate in self-luminous objects. So right now we're able to see this paper because there's light coming in from the window, and the sun is self-luminous, and this piece of paper is a reflective object. So examples here would be a piece of paper, a tree, you name it, the sidewalk. So most of the time we're thinking of reflective objects. So this is an important idea to remember, and that is that in order for our eye to see an object, rays from that object must enter the eye. I think sometimes students think that the light is coming from their eye or something, but it's important to remember that the light is going to hit the object, bounce off the object, then hit your eye, and that's how you know the object is there. That's the way you want to think about it. All right, so two types of objects, self-luminous and reflective objects, or luminous and illuminated, I think is the way it's addressed in the homework, but you get the idea. Objects that create their own light and objects that reflect the light. Okay, so two types of reflections that we're going to talk about here. The first one being specular reflection. And we're going to spend most of our time talking about specular reflection in this chapter. And this is reflection from a smooth, shiny surface, for instance, a mirror or polished metal. A mirror is a piece of glass that has been silvered so that it's reflective. And that's how we want to think of that. So this forms an image according to the law of reflection. The law of reflection is pretty simple. Let's go ahead and jot it down. It says that theta I is equal to theta R, and this is the angle of incidence is equal to the angle of reflection. And this is specular reflection. All right. I wonder if I want to tell you about diffuse reflection next. I'll show you specular reflection first. So I'm going to go ahead and take this piece of paper, and I have a mirror here. I had to turn a light on, and you can see it's a very high-tech setup. It's a ruler with an iPhone. Hi. I can see you. You can see the fan. You can see the light. And anyways, what we're going to do with this piece of glass here is I'm going to go ahead and hold it just like this over here. And I'm going to draw a normal line from this mirror. So just 90 degrees to the surface. And sorry for the shadow there. So I'll go ahead and label that a normal line. In this chapter, we like to call the normal line the principal axis. And what I'm going to do is I'm going to take we're going to test this law of reflection, right? So what I'm going to do is try and draw like about 45 degrees, right? Just pick an angle. And light is going to come in this way. So we'll call this theta incident. If you don't want to write this down right now, you don't have to, because I'm going to have another drawing I'll show you here in a second. All right, so I'm going to go ahead and try and have this leave at the same angle, right? Because theta I is equal to theta R, theta reflected. And notice here that I'm making these angles with respect to the normal, right? I'm ignoring this angle over here and this angle because they don't matter. All right, so what we'll see when I shine the laser pointer, we can see if I do it right, right? If I drew my lines right, oh, it's decent. All right, that theta I is equal to theta reflected. Check it out. Yeah. All right, very cool. And you might say, well, that's because you picked 45, right? All right, let's try it with a more extreme angle, right? Let's do it one more time. And this time I'll go ahead and I'll draw my principal axis like this, and then I'll pick some more extreme angle, maybe like something like this, much larger incident angle, and then try and draw, if I can draw this. I'm just kind of eyeballing it. All right, so something like that. Let's see. Yeah, look at that. So even the more extreme angle, theta incident is equal to theta reflected. Very neat, very cool. All right, so, all right. Let me go ahead and just point that out one more time. So this is theta incident. This is theta reflected, and this angle doesn't matter. All right, so and the same with this angle right here. And I think on some of the tests that I give, a question like this will show up where you'll have a choice between angle A, B, C, and D, and the question will be, well, what is the reflected angle? And you would pick B. Or what is the incident angle? You would pick C. And angle D and A are not choices. It's raining out right now. I don't know if you can hear that, but yeah. All right, so there we go. Pretty cool. I'm gonna pause it right there. Okay, so I think that helped get rid of the shadow a little bit. Got another light on. But you can see here that this is an example of specular reflection. So let's go ahead and go back to our notes and talk about the law of reflection just one more time to make sure we got it solid. So I went ahead and drew a perfect drawing here, and you can see even when the reflective surface is down here on the bottom, that the angle of incidence as the light ray comes in like this is made with respect to the normal being 90 degrees from this reflective surface. This is like me having the mirror right here, right? All right, and then angle reflected being theta r right here. So I went ahead and then wrote out some nice definitions here. So the normal dotted line drawn 90 degrees to the surface, angle of incidence, angle between the incident ray and the normal, and angle reflection, angle between the reflected ray and the normal. Okay, so I'll let you write that down. If I'm going too fast, you can always pause it. Or if I'm going too slow, I think there's a way to speed it up on YouTube. So you can watch me at 2 times and be like, yeah, all right, give that a shot. All right, so diffuse reflection. So most objects don't involve specular reflection, right? Most objects aren't going to do this. And if they did, we would notice that more, right? So a rough surface, right, involves diffuse reflection. So paper, skin, grass, surfaces that aren't polished, aren't super smooth, are going to use diffuse reflection. And diffuse reflection doesn't form an image. But objects can be viewed from all angles. And that's important to realize. Whereas with specular reflection, I had to have, right, the mirror sitting just right and the laser pointer just right for you to see that. Because otherwise you wouldn't see it, right? Now you can't see that. But if I point it just right, you can. So diffuse reflection, it doesn't matter. And so let me show you what I mean. So this paper right here is going to reflect light, right, diffusely. And so I'll just shine the laser pointer on the piece of paper, and it creates a dot here where the light is, right? And I can see the light even if I move my head over here, my eye over here, or if I go stand over here and I'm looking at it from over here or over here. The dot is always going to be there, right? And it's the same with this pencil, right? And the light is reflecting off this pencil. And if I stand over here, my hand is right over here on this side, I can still see the pencil. And if I stand over here on this side, I can still see the pencil. So it doesn't matter where I stand to view the pencil, right? Obviously, there's a little less light over here because I have this desk light on right now. But it also doesn't form an image. I don't see the light coming off the pencil and making the image of a pencil somewhere else, right? Or the image of or the light from the desk light isn't coming off here and making a light beam that's leaving the object. So, all right. So let's go ahead and add a little bit more then and talk about how this happens. So each ray that hits, say, this pencil obeys the law of reflection at that point. But the irregularities in the surface cause the rays to leave in a lot of different directions. So we can't tell that this pencil isn't perfectly smooth, but it's not, right? And that is why something like diffuse reflection works. So what we see, if we draw the pencil surface, right, we actually have a fairly irregular surface. And each of these light rays that's maybe coming in like this, right, is going to be reflected off in a different direction according to the law of reflection. So the law of reflection still works here, but because of these irregularities, you get different normal lines, right? So the normal line maybe at this point right here extends this way, and the normal line at this point goes this way. And so theta I and theta R are always relative to the normal, and so you end up with this scattering effect, and you don't get all the light being reflected perfectly like you do in specular reflection, where you have a surface like this and it's reflecting the light perfectly. All right. Okay, very good. Let's go ahead and move on. So, all right. So the next thing I want to do is to do a little demo here, and so what I want you to do is to find a sheet of paper. It doesn't have to be, I guess it should be a blank piece of paper. It could be lined. It doesn't matter, but just something you can write on. All right, and you're gonna fold it, so something you're not too worried about. So what we're gonna do is we're gonna write the word cat, and then you can pick any word. I'm just trying to pick an easy word. So I'm gonna fold my paper in half. What is this, hamburger? I think it's hamburger, yeah. All right, I'm gonna fold it in half, so I want you to do the same. All right, very good. This is part of your assignment, so you have to do it. So I want to make sure you're doing this. Okay, so anyways, fold your paper in half. All right, very good. Then let's go ahead and unfold our paper. And you can see there's this line here. We're going to use that line because that's going to be where our mirror is. So we're going to pretend that that's our mirror. What do I mean by that? Well, just so I maybe so you don't forget, I can draw a blue line right there. So that's going to be the mirror. Why blue? I don't know. That's the color I've always picked for my mirrors. I guess I think there was a Vsauce or something on YouTube, and they said the color of a mirror is actually slightly green. But anyways, okay. So we'll go ahead and then write out a word, and I'm going to pick the word cat because it seems easy enough. So we're going to write it at an angle like this, and we're going to write it kind of large. So and maybe I'll pick uppercase letters just to make our life easier. All right, pretty good so far. Trying to write it neatly as well. Okay, so very good, cat. Okay, so now according to the law of reflection, or how this works, we're going to, if this was a mirror here, we're going to go ahead and work off the idea that for a flat mirror, like this one right here, a flat plane mirror, the distance from the object is the same as the distance to the image. And so what I'm trying to say is this. I'm going to pick some points here. Let me see. I got so many papers here. Straighten this out a little bit. So I'm going to pick some points for a letter. So for the letter C, let's pick these points right here. 1, 2, maybe we'll pick another one right here, about as close as it's going to get to the mirror, and then maybe another one right about as far away as it's going to get to the left, about right there. Okay, and what I'm going to do is take a ruler. You don't have to have a ruler, but it makes your life a little easier. And then I'm going to measure this distance, because the distance to the object, right, looks like this is about 3.5 millimeters. So if I go from the mirror 3.5 millimeters, so I'm at 3.5. So if I go 3.5 more, that'll get me to 7. And I'm going to make a dot right there. So what I'm doing is drawing where this reflection would be. So I'm saying that this dot is 3.5 away from this dot. So just maybe so you can see this a little better, I'll go ahead and draw some lines just so you can see what I'm saying. So I'm saying that this distance to the object, right, d sub o, we'll say, is equal to the distance to the image in the mirror. And that's kind of the basic idea I'm going to use to try and draw the reflection. All right, so let's go ahead and do the same thing for this dot right here and repeat this for the other two dots. Okay, so it looks like this is about 5.5 away. And so from here, I'm going to go about 5.5. So there's half, gets me to 6. 5 more should be 11. Okay, now ideally I would do this for all the dots in the object, but I'm gonna, I'm trying to make this, I'm trying not to have this take so long. I think something more like that, right? And so what I'm drawing is this right here, right? Is this right here. And I believe I'm doing that correct. I can check, with another dot. I should have another dot about the same distance away, about right there. So, ooh, that wasn't so hot. All right, so about right there. Whoops. And so you can see I'm going to do this over, make it a little bit better. I'm going to get rid of this image, or this line here, just for a second, because I don't want you to think that that's the letter C. So this is the reflection of this part right here. Then I'm going to go ahead and get another, I'm going to do another one right here. We'll say, just pick somewhere. All right, and this one's obviously very close to the mirror. This looks like it's about 1.5 away. So I'm gonna go 1.5. Was I saying millimeters before? I meant centimeters. I'm sorry. So there's 0.5 centimeter, and there's one more. So about right there. And so what we're saying is this reflection is gonna look like this, right? Okay. Hopefully you're able to do this. Well, this one's pretty easy to do. I'm just gonna go ahead and draw it right in, right? I don't know what that is. Probably 0.5 centimeter, and then this is this right here, right? Okay, cool. All right, this is like art class. All right, so then we're gonna make this shape right here. And so to do that, right, I'm gonna use some dots. So how far away is this one? Well, it looks like 1, 2, 3, perfectly, 3 centimeters away. All right, 1, 2, 3, so about right there. And this is going to just go, I think I can do it, right? It's going to go like this. Okay, so far so good. And I have my reflection for the letter C. Okay, so I'll help start the letter A, and then maybe I'll pause it and let you finish it up. But for the letter A, I would maybe start with these 3 points. And maybe that's going to be enough, but probably not. All right, so I'm going to start with these end points, right? In kind of this triangle shape. So I'll first measure this one. And like I said, it doesn't have to be exact. I'm just trying to make it better, you know, than, all right, so this is, what, 8.5 centimeters? Okay, so if I go a half more and then 8 should get me about to 17. Once again, if you don't have, whoa, all right, so it's that far away. Now this one's going to be shifted over this way, right? So I'm going to go ahead and measure this distance right here. Looks like about 3.5 centimeters. So I'm going to go 3.5 centimeters into the mirror, right? So get me to about 7 right there. And what you can see is that this connects just like this. The same thing's going to happen here, where this is going to the right, this is going to be going to the right, and I'm just going to use my straight edge from my ruler to draw that, right? That it's going to travel just like that. And then finally, I'll get this dot, and this one looks like it's going to be about 5.5 centimeters away. So I'm going to go 5.5 down this way, which will get me to 11. And then I can draw and connect like this. Now this line's kind of tricky, right? So instead of just, well, maybe I could guess. I better not. I better just pick some points. And that's kind of the idea, right? Like if you can't figure out, if you can't guess, then pick some points and make the measurement, and draw your straight line, and it'll work. This is about 6 away, 6 away, 6 centimeters away, gets me to about 12, about right here. And then this one is going to go up. So it's going to go up. And see, I was going to draw that wrong. All right, so this is going to be about 7 away. And so 7 away from here is going to get me to about 14. And it should go up, right, if I did it right. Okay, just like that. And you can see the word starting to take shape, right? And okay, so I guess I might as well just finish the rest on camera, because we're almost done, and T isn't that hard to draw. So T will go ahead and take 1, 2, 3, 4 points, right? And this is where, being so far away, I think it helps to have that straight edge here to help with, or a ruler is the best thing. All right, so 10 centimeters in, 10 centimeters in. I got 1 point right there. This one looks like it's about 12 centimeters away. So I'm gonna go 12 centimeters away. Gets me about right there. And then this one's about as at the edge of the page practically. And my paper is getting a little hard to deal with. So this is about 13 and a half. So 13 and a half downward should get me to about 26. All right, and you can see it's not perfect down here. And so I'm gonna have to do my best with that and try and draw that straight line between them. We'll just say that there was a little bit of experimental error right there. Okay, and then we'll go ahead and measure this last point. Looks like that's about 7.5. 7.5 gets me to 14. No, 15. Yeah, 7. Okay. So we're saying something like that. Try and line this up. Somewhere I wasn't exact enough here. All right, so what did we make? Well, we made this, right? You might say, well, that's kind of nonsense, right? But the idea is, what we're going to do is we're going to take this and hold it up to a mirror and see if we can see the reflection in it. So what I'm saying here is if we hold, I don't know if I can get this on camera, if we hold that up to the mirror, we should be able to see the word cat. Oh, awesome. All right, so take your word, your gibberish looking word over to the mirror and see if you can do that. Now, obviously I could have picked a tougher word, right? And I usually tell students pick a word 3 to 5 letters and then they pick tougher, they pick 5-letter words and then they get upset. So anyways, give it a try. All right, I'll go ahead, or why don't you go ahead and pause it there, do that, and see if your word looks the same in the mirror, and then we'll continue. All right, so we'll do one more drawing before we get a definition of virtual images, real images, and whatnot with a flat mirror. So this next drawing, what we're gonna do is we're gonna go ahead and draw a mirror. We'll have it just be this line. I guess I can use the color blue since I told you my mirrors are blue. All right. And what we're then gonna do is we'll draw a surface. Go out a little further. And we're gonna go ahead and sketch a pencil. Let's see. Maybe something like this. And it's not bad. All right, something like that. So we have a pencil here in the mirror, or in front of a mirror, and what we'll do after that. Let me see if I can get some different color markers here. Is draw a ray coming from the top of this pencil. I'm just going to pick a point on the pencil, and then I decide to pick the top of the pencil, and I'm going to have it go straight at the mirror and hit the mirror. All right, so when this happens and the ray hits the mirror, it's going to follow the law of reflection, and so we know that there is a normal line 90 degrees to the surface, right there. Now, what is the angle of incidence right here? Well, you would say it's 0, right? Because this incoming ray makes no angle with the dotted line. They're on top of each other, right? And so what I'm going to do is reflect then this incident ray straight back. And let me see if I can draw this without. So I'm saying it's going to reflect straight back like this. And it might be slightly staggered just so I made it a little more visual that way, but it should just be right on top of that ray. So this ray comes in, hits the mirror, bounces straight back. And I'll call this ray 1. All right. Now I can do this at any point, right? I didn't have to pick a mirror or a ray going straight at the mirror. So let me just pick a point. Maybe I'll pick a point, and once again from the top, right? Because there's an infinite number of rays coming off of this point. And I will pick, I don't know. Maybe I'll try for about halfway down, something like that. I'm using different colors here just to make this a little more visual, and hopefully that's helping. All right, so then what I know, according to the law of reflection, is that there is a normal right here. Notice I'm always drawing the normal where this hits the reflective surface. I'm trying to draw it normal. Dotted line's getting a little crazy. All right, so there's my theta I. And I know that there is an equal angle, there's an equal angle that it's going to reflect off of, right? The theta I will equal theta R. Okay, so I'll try and draw that in with my straight edge. Oops. Obviously this isn't perfect, but I'm trying the best I can. All right, I'm sure your drawings will look much better. All right, theta I is equal to theta R. And I'm going to call this ray 2. Now the image for this pencil in the flat mirror is going to be the same distance away. So we expect if the pencil, right, is right here, right, there's a giant number 2 pencil, that in the mirror, the same distance away is the number 2 pencil. But how do we see it? How do we predict it with the ray diagram, right? This is a ray diagram where I just draw a couple rays, even though there's an infinite number of rays coming from that point. Like I could have kept going and drew a third ray here and a fourth ray here and so on, and I just didn't want to keep doing that. All right, so I think 2 is enough. So what I'm going to do is I want to know where this image is, right? Or I want to be able to predict it. Let's say maybe you didn't understand that it's the same distance away, and maybe you want to know the height of it, right? And so there's other things to learn. So what we're going to do is we need to know where ray 1 and ray 2 meet. And we might say, well, if one person starts walking this way, another person starts walking that way, they would never meet, right? So what we have to do then is in a situation like this is we have to look at where ray 1 and ray 2 appear to come from. Not where they actually come from, because they come from this point right here. But where do they appear to come from, right? They actually appear to come from, if I follow, say, ray 2 back, and I line up my straight edge, ray 2 appears to come from back here, right? And ray 1 appears to come from, let's see if I draw this, appears to come from, well, ray 1 goes like this, it appears to come from back here. And I think you can see where I'm going with this, is that where ray 1 and ray 2 appear to come from and meet, that is where the image is, right? So I can go ahead and draw. Now you might say, well, what point of the image? Well, it would be the top of the pencil head, right? It would be that right there. And the rest of the pencil would be right there. Okay, so it looks like I did pretty well with with height, right? And so but not so well with distance, right? Distance to the object should equal the distance to the image. So let's go ahead and write some of those in. So this, hopefully your drawing's way better, because obviously mine is not so great. And I'm looking at maybe these angles were slightly off. I think my theta r is a little too large. I think if I would have had it be a little smaller, that it would have met at my pencil would have been back here a little bit. So yeah, really with a ray diagram, you really got to be careful there. So anyways, this is going to be my distance to the object, and from the reflective surface to the object, or I'm sorry, the image is going to be my distance to the image, or di. I'm going to go to the middle of the object. Okay, and then from the, I guess the ground, sometimes we have to use the principal axis there, to the top, this will be my height of the image, hi, and this will be my height of the object, h sub o. All right, so you can see we have height of the object, distance to the object, distance to the image, height of the image. And these are all, height of the object is equal to height of the image, and distance to the object is equal to distance to the image. Even though that looks gross on my drawing, that's correct. Okay, so let's go ahead and get some definitions there for a flat mirror. So first thing I want you to realize about a flat mirror is that they form a virtual image. And this means that the light rays don't really pass through where the image is. So this is an image formed in the mirror where divergent rays, right, ray 1 and 2, we're never going to meet, they're diverging, appear to come from. So that's how we know it's a virtual image. A virtual image won't appear on a screen, so you can't stand behind the mirror and hold up a white piece of paper and say, where's the image of the pencil, and look for it, right? It's not going to appear there. An object's virtual image is said to be at this location because the light appears to come from there. So that's what we're working off of. So when we label something a virtual image or a real image, it's not so much about what you see in the mirror. It's more about, did the light really go through that point? Real image. Did the light not go through that point, but it appears to come from that point? Virtual image. And that's what we're going with there. Because both of them are going to be able to see in the mirror, but mirrors actually will make images outside of the mirror, and we call that a real image. And that's kind of weird because you might say, well, I've never seen a mirror make an image outside of a mirror. Well, yeah, because the ambient light gets in the way and it's too bright, and it knocks out the image so you don't see it. And it happens for curved mirrors. So I don't think, unless you spend a lot of time with curved mirrors, you probably wouldn't notice it. So anyways, for a flat mirror, di is equal to do, even though on my drawing it was kind of rough. And then hi equals ho. Okay, so there's actually different variables sometimes that textbooks use. I think they use like p, q, and r, or p and q at least. And I think d sub I, d sub o, and h sub I, h sub o is just way easier, so I stick with those. All right. Okay, so I want to say something about real images then. So I kind of hinted at this, so I want to go ahead and explain that. A real image then forms where light rays converge on a point and actually pass through that point. So the light rays would meet and converge on a point, right? And this would be outside the mirror, and we could hold up a screen and see. We could hold up a screen and see the real image on the screen. and it's something that can be done, especially when you have an object that is self-luminous, and it gives off light, and you have the ambient light turned down, so you're in a darker room, and you can actually see the image on a screen or a white piece of paper or something held up. So this is a real image, but the point to realize is that the light rays really pass through that point. They converge on a point and outside of the mirror, and the light rays really pass through it. Okay, I'm going to pause it there, and then we'll talk about curved mirrors. All right, so we're going to talk about some curved mirrors, and then the different types, and then we will go ahead and do some example drawings, some ray diagrams, and go from there. So a curved mirror is a silvered piece of glass that is reflective, just like a normal mirror, but it's part of a spherical mirror. Is probably is the way you want to think of it. So it's like if you have a sphere, right, like this. This is a circle, right? You're just thinking of a segment of the circle. Is kind of what we have there. So it can be concave or convex. And so what I've drawn here is an eye looking into a concave mirror, and I went ahead and labeled the principal axis right here. But you can see that I'm thinking about the mirror as being part of a sphere, right? And the same is true for a convex mirror. That now we're looking at the outside of the sphere, right? And so this is convex, and when we're looking into a cave, this is concave. This is, you can see I just dotted line the rest of the sphere. The principal axis, notice though, is on the inside, right? Because if this is part of a sphere, then you can think about the fact that the center of that sphere would be right here. And the same would be true over here. And I'm going to talk about this in a second, but this distance right here would be the radius. And half of that distance would be where there's a special point called the focal point. And the same is true over here. And half of the radius is the focal point. Okay, so examples of concave and convex mirrors. A beauty mirror, when you look inside of a sphere that's curved, this is how you get a larger upright image. Now, it's going to depend on how close you are to the mirror, because some interesting things happen with the beauty mirror. I notice I wrote the inside of a spoon. Let me see if I can grab a spoon here. So you notice that the inside of the spoon, I appear, you can see my image there, I appear upside down. So it's not till we get close enough that it starts to flip. And you can try it at home yourself with the inside of a spoon. But you have to, in order for this image to change where it's right side up, you have to get it pretty close to your eye. So be careful there. You don't want to poke yourself in the eye with a spoon. All right. So a convex mirror would be this side, right? And notice I am upright already, right? And I am right side up, right? I'm looking down at you, and I am already right side up. Whereas the other way, I was upside down. We're going to talk about why that is, right? So anyways, this is convex, like I'm looking at the outside of the sphere, right? And here, concave, I'm looking at the inside of the sphere. Okay. Where do we see convex mirrors? Convenience stores, where we notice they might have them going around corners, hospitals going around corners, something like that. Car side view mirror, side view mirror of a car, another place you could see a convex mirror. All right. Good. So two types of mirrors, concave and convex. Let's get a little bit more here about these different points. The first is the point C. C is the center of curvature, right? It's the center of the sphere. So the distance from C to the mirror is the radius of curvature. So you can go ahead and write that down. I said that half this distance is a special point called the focal point, and then that half of the radius is also called the focal length. So I'll go ahead and write that down. And then I will have it in a drawing here below in a second. I'll show you. So this point F, this focal point, if light is coming in from infinity, so light from a distant object comes in, hits the mirror, its image will appear at the focal point. But the opposite is true too. So meaning that if you are at the focal point of a concave mirror and you stand right at the focal point, right, and you get close enough where you're at the focal point, notice the image disappears, right? So when the object is at the focal point, there's no image. And I'm going to come back to that here in a second. Whoops. I'm going to come back to that here in a second. So the focal length is the distance from F to the mirror, which is half the radius of curvature. Okay. Once again, drawings, just to show you what I'm trying to say here, is you can see that the radius is from C to the mirror, and from F to the mirror is the focal length. And once again, the person's eye is on looking into the cave, and the person's eye is from outside the sphere, but we still draw F and C on this side, where the sphere is. Okay. All right, let's go ahead and move on then. So rules for curved mirrors. Now, curved mirrors still have follow the law of reflection. And what is worth noting here is that although theta I equals theta R, we're going to see different images than we would see, say, on a flat mirror, because the normal is different at every point. And so what I'm trying to say with this is the normal changes, right? I think it might be easier if I grab this mug and show you from this mug. So this is a spherical mug, and that's kind of tough to see. Let me see if I can take these pencils out. Oh boy. Oh, there's one marker in there. Okay. All right, so anyways, with this sphere, right, the normal is going to change. Right here at this point, the normal is going to be straight up. Whoa, I cannot draw a straight dotted line to save my life there. All right, so it's going to point like that, like the pencil, right? And as I go around the mirror, the normal always points 90 degrees to the surface. Check it out. Now the normal points this way. What about here? Oh, that way. What about down here? And so you can see the normal changes with the curvature of the mirror. And that was what I wanted you to see. So curved mirrors are going to have some interesting images, but notice that theta I still equals theta R, but the normal is different at every point because it's always 90 degrees to the surface. So here are our rules here. So the rules for drawing ray diagrams for curved mirrors. Just go ahead and write this down, and then we'll talk about it here with some examples. All right. Okay, so for this next part, what you can do, right, we're going to follow these rules. I'm going to set them to the side right now. You can either go on to Schoology and download these note guides or pages here. I think there's 3. They all look similar, but they're all different. One says ray diagram for concave mirrors, and one says ray diagram for convex. There's 5 examples for concave, 1 for convex, or you can just work off of a separate sheet of paper. I'll let you decide. Okay, so yeah, I'll let you make that choice. So we're going to start with concave mirrors. So make sure it says concave at the top of your page. And notice that the first is going to be a person that is outside of C, or the center of curvature. You can go ahead and just draw this on your page if you're just taking notes on a blank sheet of paper. And we're going to go ahead and follow our rules and do the example here. But when we draw our image, we are going to draw this person. What we're going to notice is that with our rules, that we're going to, where these 3 rules meet is going to be our image, is what we're working with. There's going to be some exceptions to that, and but that's kind of the basic idea. Why do we have 3 rules? Because sometimes 2 isn't enough, although sometimes 2 is, but that's what we're going to work off of. All right, so the first one, I'm going to go ahead and grab some different color markers, and I find that helps students to see what's happening. So I'll start with green first for rule 1, and I'm going to get a straight edge. You're going to want to do the same. It could be a calculator, it could be anything, a book, but I'm going to use this ruler because it works pretty well. All right, so I'm going to always go from the top of this person's head, the top of the object, and work off there. So the first thing I'm going to do is draw a line from straight at the mirror, a ray, straight at the mirror, reflect, and then go through F, right? But I want to make sure I'm as exact as possible with these rules. And the reason is we don't want bad drawings, right? And we remember last time when I drew the pencil, it was pretty crummy at the end, and you were like, oh, DI doesn't equal DO. You say it's supposed to, but it doesn't look like it. Yeah, that was because I was careless. All right, so I'm trying to do a better job this time, but no guarantees. Okay, so there's ray 1, or rule 1, right? Straight then through F. All right, good. Rule 2 says through F then straight. So I'm going to grab a different marker just because I want to make this as clear for you as possible. So I'm going to go through F, hit the mirror, right? And that's important. You have to hit the mirror to reflect. And it kind of goes without saying, right? All right, hit the mirror, and then reflect straight back. Let's see if I can line this up. Yikes. All right. And then that's rule 2. And then rule 3 says through the center of curvature and back. And with this rule, you have to assume you have a sphere. So meaning that I'm going to try and start at the same point, go through C, and it should go through the same point where the other rays went through. Should. And what it's going to do is going to hit the mirror down here and then bounce straight back, right? So I'm saying it's going to hit and maybe right there, right? Because you have to assume it's a sphere, and then go straight back like that. Okay. Now where these 3 rays, the 3 reflections, right? Here's 1 in green. Here's 2 in red or maroon or whatever that is. And then 3 right here in blue. And where do they hit? The reflected rays, not the incoming rays, right? I don't care about those. I care about the reflections. 1, 2, and 3, well, they converge on this point right here. And the reason that's important is because that is the top of the image's head. And the rest of the person's body is right here. All right, something like that, right? And so you can see that this would be, you can think of this line right here as being the principal axis, right? This midline. It just so happens that it's the ground where the person's standing, but it doesn't have to be. Because I know in the assignment there's a problem with a object that is through the principal axis, right? So it doesn't have to the person doesn't have to be standing on the principal axis. All right. Anyways, let's look at this image, right? Check it out. First of all, location. We could say between C and F, right? I'm going to use lowercase f there for focal point. Upright or inverted? Well, upside down, right? So we're going to go inverted. Magnified or reduced? It does look like the object is larger than the image, so I'm going to go with reduced. So the image is smaller. Real or virtual? Do the light rays really pass through this point? Yes, right? So we're going to go ahead and say real. Okay, that's it. Let's go ahead and go to the next one. All right, this is a good test because when the object is at C, the image should be directly under C. So it should be right here, right at C. So let's go ahead and see if we can do this. If you want to pause it and see if you can remember all the rules and do it on your own, go ahead. That'd be a good test to see if you remember. I'm going to go ahead and do it, and then we'll talk about it here. So my first rule is going to be straight at the mirror, and then we're going to reflect back through F. Okay, and then we're going to go through F. Notice I'll label these. Notice I picked my other color marker. Oh boy, that's not a good sign right there. Already kind of missing F a little bit. Ugh. Oh well, we'll find out. I like this one because, like I said, if you screw it up, you know. Because it should appear right under C, where the object is standing. Oh yeah, that's not going to be great. It's not, maybe. Okay. Oh. I think I might have cheated a little bit. And we can't really do rule C here, or rule 3, where we're going through C and back. I guess we could go that and it would still work, but 2 is going to be enough here. So decent, right? I'm going to go ahead and draw the person's face, because remember, I know this is where the top of the person's head is. Here are the person's feet and arms. All right, so we can see right there, upright or inverted. We would say, well, it's upside down, so inverted. Location would be at the center of curvature, or at C. Magnified or reduced, we would say, boy, I don't know, right? Like, I don't think we can say either. So we're going to go with equal. All right, I'm going to cross those off. Real or virtual, do the light rays really go through this point? Yes, they do, so we're going to say real. All right. Okay, so in case 3, you notice we started with case 1, we were outside C, and we were at C, now we are between C and F. We'll go ahead and do the same thing as before. Once again, grab your straight edge. Start with straight, right at the mirror, and then reflect through F. And we'll go through F, label that 1, through F, then straight. See here. All right, that one's coming down quite a bit lower. All right, I think it's gonna about do it. And then through C and back. And you can tell I didn't go far enough with the first vector. I'm probably gonna have to go back and fix that. Let's see right there through C. But like I kind of mentioned before, you really only need 2 of these, but I like doing all 3 because in some of the cases, some of the rules are invalid. All right. So that's rule 1 right there. All right, so you can tell though that the image of the object is going to be right here, that the top of the person's head is going to be right here. And you can also, I think, tell that the object is going to be larger and beyond C, right? So we can say location beyond the center of curvature. Inverted, magnified, right? Larger, and then real, because the light rays really pass through it. All right, let's look at case 4 next. All right, let's go ahead and move up here. So case 4 is we're going to be at the focal point. Remember what we said about the focal point, right? When an object is at infinity, the image is at the focal point. But when an object is at the focal point, then the image is at infinity. So we expect not to be able to see an image here. Let's look at why that is. So once again, just following our rules. First one, straight at the mirror. Then through F. All right, so the first one's fairly simple and straightforward. Just got to line it up. All right, the second one is through F. All right, and if you went through F, you'd have to go straight down and you wouldn't be able to hit the mirror. So we're going to go ahead and have no rule 2 here. So this is rule 1. And then because we can't go through F when we're at F, I'll just write it right over here, no rule 2. Okay. So then the final rule, right, we only need 2 rules for this to work, was through C and then back, right? Like you're hitting the mirror over here and then going straight back. And you notice if you do it correctly, what you'll notice is that these 2 rays are parallel, right? And that they will never hit. So and they won't hit back here if I dotted line them back, and they won't hit here. So we can go ahead and answer these questions then. Oh, and it says no description required. So we could say image at infinity, right? The infinity sign. I'll write it out. Or you could say no image, right? Okay, so no image or image at infinity. Okay. All right, good. Last case. So we were between C and F. We were at F. Now let's go ahead and move inside of F. And this is going to be what happens with beauty mirrors. Remember how we said concave mirrors are the mirrors you'll put like on a dresser or something? This is why right here. So let's go ahead and try our rules here. So rule 1 was straight, then through F. Here. Okay, and even though the object is in the way, we can still make this happen and still draw this, and it's not a problem. Okay, there's our rule 1. Rule 2 was through F, then straight, but we can't hit F and then hit the mirror. All right, we still got to hit right here, even though we sometimes like to think of it as a sphere. So what we're going to do here is we're going to come from F and hit the mirror. So this one's okay. I guess the problem you might run into here with this one is that, let me see if I can come from F. So I like to use a dotted line right there, then a straight line at the mirror. So, so something like that, right? And what did I want to add there? I'm going to go ahead and draw this line first. And it's kind of tough here because it's not really curved like a sphere a ton. So I'm going to come from F and go straight. So I get something like that. Because remember, this is supposed to be like a piece of a sphere. And so it's kind of hard to tell the curvature right there. So it's not great. All right, there's rule 2. There's rule 1. Okay. And then finally rule 3, which was through C and back. All right, so here's C. Try and line this up. Not great, but okay, and there's rule 3. All right, but it's pretty obvious here, though, that all 3 of these rays, 1, 2, and 3, are never going to hit, right? So remember what we did when we ran into this case before, right? We said, well, where do the rays come from? Well, they come from right here, right? But where do they appear to come from? And so what we do is we follow them back. So we'll take ray 1, right? We don't want the incident rays, we want the reflected rays. So ray 1, the reflected ray, I'm going to dotted line it back. So I'm going to line up my straight edge right here and dotted line where it appears to come from. Like that, right? And then I'll do the same thing with ray 2, which is easy because it just is a straight line. And this is, kind of like what your eye perceives, right? Your eye only can understand the rays in straight lines, so it thinks it's coming from back here, right? And then finally, rule 3. This is looking all right. Okay, let's see. See if I can do this one. Bit of a mess. Ugh. It's tough because using these markers and... Okay, you get the idea. I mean, you can see it, but I was just trying to make it look good. All right, so looks like about right here, right? And so what we can see is, you can think of this principal axis just extending through. So what we can see is that this object, because the object's going to be related to the principal axis. I don't know what I'm doing with this drawing. Oh, I gotta go lower. Get there someday. Okay. So you get something like kind of like that, right? Okay. All right. Pretty neat, right? Okay. So, let's answer some questions about it, right? First of all, location. We would say behind the mirror, on the virtual side of the mirror. I'll say behind the mirror. I guess I like that. Upright or inverted? Obviously upright. Magnified or reduced? We'd say magnified. Real or virtual? And do the light rays really pass through this? No. So we're going to say virtual. All right. And that was our final case. So when the object is inside the focal point, upright and virtual. When the object is at the focal point, no image. When the object is between C and F, larger, and outside of C or beyond C. When the object is at C, we say the image is at C as well, real and inverted. And then finally, when the object is beyond C, we get the image between C and F, but smaller and inverted, or reduced and inverted. Okay, so when we look into a spoon, this is what is going on, and this is why you're upside down in the spoon, unless you get it really close to your eye, and then you can, you should see it flip, is the idea. Okay, so let's go ahead and go to convex mirrors now. So the rules for convex are going to be the same, but we're going to go ahead and see, notice some things right away, right? That C and F are inside of the sphere, right? So we're not going to be able to hit them. Now, it's not going to stop us from trying, and that's what's important to remember here. So the first rule was straight then through F. So we'll go straight at the mirror. Let me see if I can line that up. Oh, geez Louise. I was doing so good. There, that looks a little better. All right, straight at the mirror. And then since we can't go through F, we're going to come from F. So I'm going to line up F with this point right here and reflect this direction, just like that. We'll call that 1. All right, next one was through F, then straight. So once again, we're going to go at F. And it's right there. Find the top of that person's head. Oh, why can't I do it? Right there, maybe. All right. Kind of finicky. Okay, so we can't hit that point, so gotta be careful. So I'm going to go at F, right? And then I'm going to go reflect back straight. And I always try and line this up to the principal axis there. And that way I'm kind of hoping I'm, fairly accurate with these lines and not get my parallel. Like this line should be parallel to this line. And so I try and do that to help. Otherwise, the drawing gets kind of crazy. All right, and then finally through C and back. So once again, we can't hit C, so we're going to go at it. line up C with the top of the person's head. You go add it and bounce back. So I'm saying something like this and this. All right, and so you can see we're in the same predicament we were before. 1, 2, and 3 will never hit. So what we do is we look back behind the mirror and see, well, where do they appear to come from, right? And if we remember, well, rule 1 appears to come from F, right? If I can line this up. I guess I'm just trying to make it look good. I could probably just do a dotted line freehand. Right? It appears to come from there. Where does rule 2 appear to come from? Well, rule 2 appears to come from this straight line right here, right? Right here, right? And then rule 3 appears to come from C. Try and line this up. All right, right there. And so you can see it's fairly obvious where this image is going to be. So we put these mirrors in party stores or convenience stores because you can see more in them. And it's going to be upright. It's going to be upright. We never have a flipped image in a party store, right? Location is going to be between the focal point and the mirror. You know, could I say behind the mirror? I think it's best to use this description of maybe C and F and use those. The fact that it's virtual is going to let us know that it's behind the mirror. But anyways, so it is a virtual image. The light rays don't really go through that point. Magnified or reduced, well, here's the person's height. Here's the new height. So obviously reduced. Upright or inverted, well, upright. Once again, no inverted images from a party store, convenience store mirror. Okay, same with, you know, a side view mirror in a car, right? All right, so let's do it again. This time we're gonna push the person out further, and should that matter, right? If you go into a convenience store or wherever and you stand further from the mirror, does that matter, right? These mirrors are great for showing us a lot of showing a lot of objects all upright, but is it going to matter if we stand further away? And most of us will be like, no, heck no, it doesn't matter. So let's try it, right? Let's try our rules and see what happens. So let me see if I can find my markers here. All right, so first one, and you can try this if you want to pause it and try it on your own without my help, you can. But I'm going to go ahead and go through it. All right, so first rule was straight, then through F, but we can't hit F, so we come from F. Call that rule 1. Rule 2, we're going to go through F, then straight. Can't hit F, so we're going to go at it. Going a little faster this time. Why did I dotted line that? I don't know. All right, through F, then straight. All right, doing the dotted line thing again. You know, once I start making dotted lines, I just want to keep making dotted lines. I don't know what else to say. All right, so that'll be rule 2. And finally, rule 3. we're going to go at C and then reflect back. So this one's tough. C's so far away. Like that. All right, and you can see we're in the same predicament we were up here. All right, so let's go ahead and dotted line those back. I'm going to try it without the help of the straight edge. I think I can do it. My hands are steady enough. All right. 2. This is a straight line. All right, and then 3. This is going to be the hard one. I think I'm going to go ahead and cheat and use it. It's not perfect, right? This is a model. You know, I know I tried to make it perfect, but it's not a mathematical equation, which we will actually get to next time. Oh, my drawings. All right, so it looks like, if anything, by going out here, what happened to the image that was different than before? We might just say it's further reduced, right? Reduced even more. Notice it's still between F and the mirror, right? Upright or inverted, we'll say upright. Magnified or reduced. Reduced, I might write further compared to case 1. All right, and then real or virtual. Well, light rays don't really pass through it, so virtual. And that's it. So how many have any other? Yep, that's it. Those are all the cases. So so there you have it. Hopefully this is making a lot of sense. So convex mirrors, another example of a convex mirror, I just realized I didn't mention before, is a Christmas ornament, right? So when you look at your self or your reflection in a Christmas ornament, you would see a smaller image, upright, virtual. So 2 examples of convex mirrors, but really only one case, right? Because they're kind of the same, except if you stand further away, you're even smaller. And then 5 cases for concave mirrors, and that's about it. So, all right, as far as homework, this week, what you're gonna have, I kind of didn't give you a lot last week, so I'll try and make up for it this week. A little bit of electromagnetic spectrum work, you know, remembering which type of waves have higher frequencies or longer wavelengths or more energy. Remember, the L's are on the left, lower energy is longer wavelengths, and lower frequency all on the left. Law of reflection right here, and then some examples. Looks like convex mirror, just a flat mirror, like we did with the pencil example. Hopefully you can get a better virtual image than I did. Concave, looks like this is C, right, where R is, right, which is not called C, it's called R, that's fine. It's still the center, or that's, you know, the radial distance there, the center of curvature. Inside the focal point. And then finally, check this out, right? See the person standing. So because half of their image is underneath the principal axis. And when you think about how that would look, or the half of the object is underneath the principal axis, think about how the image would look, right? So always make sure you draw your image when you're done in relation to the principal axis. So do not just draw the points going through a point. Be sure you draw that arrow right here. I don't know why it's an arrow. If you want to go through and make this a person and a person and a person, or a pencil, you can, and that's fine because there's already enough arrows going on. I didn't write this worksheet, but it's still good and we're still going to use it. We also have this worksheet right here, which deals with light reflections. So some examples, and I like this one here on the bottom about why I think you don't notice reflections in the earlier part of the day, but you notice them in the later part of the day with the sun and windows. And then this right here, if you think about this, I think you can do it. I think you got to draw a normal line, and it's not bad. You do not, let's see. I'm not sure if I want you doing this last question or not. I don't remember. But I don't think it's terrible. I think it's all right. So maybe I'll just leave that on there. All right. Anyways, have a good week.